Welcome physics students to Juddy Productions, and in today's video we'll be looking at a sample calculation involving the process of fusion. So you see on the screen at the moment there's multi-step processes in terms of the fusion occurring in the Sun, and this particular reaction is one of the three on the screen. A reminder that today's video is one in a series of three. There is a video on nuclear fission involving mass defect and energy calculations. There is a second video on alpha decay equations, also involving mass defect and energy calculations. And of course today's video is mass defect and energy calculation with nuclear fusion. So consider the following nuclear fusion reaction and associated data. So we have here a nuclear fusion equation, talks about a hydrogen 1 plus a hydrogen 2 fuses together to generate helium 3 and energy. And we have the 1, 2, 3 different masses of each of these isotopes presented in kilograms. Our task for today, number 1, is to calculate the mass defect. And number 2 from that, calculate the energy generated from the mass defect. So first of all, task 1, let's calculate the mass defect. First of all, we have to look at the mass of the reactants, highlighted in green. So there's the mass of a hydrogen 1 and the mass of a hydrogen 2. We take that from the data provided to the left. We add that together. We get a total mass of reactants of 5.01748 by 10 to the negative 27 kilograms. We do the same for the products. There's only one nuclei product present in this equation, and that is the helium-3 nuclei. So the mass of the helium-3 nuclei, as given to the left, is 5.006942 by 10 to the negative 27 kilograms. And we note that that is less than the mass of reactants that we started with. So to work out the mass defect, we simply take away the mass of the products from the mass of the reactants, and we find out how much mass has been lost. That gives us a mass deficit of 1.05410 by 10 to the negative 29 kilograms. Extremely small. However, when you multiply this small amount of mass deficit by billion copies of this same reaction in nuclear fusion, we get a large sum of energy being generated. So there's our mass deficit. Task 2 is to calculate the energy generated. So E equals question mark. M is the mass deficit in this reaction, as we just calculated. C is the speed of light. It's 3.0 by 10 to the 8 meters per second for our purposes. Einstein's famous equation, E equals mc squared. We multiply our mass deficit by the speed of light squared, and we get a value of 9.48690 by 10 to the negative 13 joules. Again, very small for one individual reaction. We divide that by 1.6 by 10 to the negative 19. And we do so to convert our energy from joules into electron volts, which is a more common unit. So when we divide that energy by 1.6 by 10 to the negative 19 joules, we end up with 5,929,312.5 electron volts. Of course, this is more commonly expressed as mega electron volts. So to convert to mega electron volts, we're just dividing by a million, or 10 to the 6. Effectively, we're moving the decimal place 6 places to the left from our previous calculation. So that leaves us with the energy being generated in this reaction of 5.9293125 mega electron volts.